Analog continuous signals such as voltages or currents as a function of time are useful in circuit design and analog communication. But most of the signals are first converted into a digital domain, in other words, into numbers, to be processed by a computer. Calculus tools work with analog functions or signals, but the main emphasis on calculus in this course is not because of that. The results developed for signals and systems using calculus tools are elegant and easy to understand, while similar development for discrete and digital signals would be cumbersome and difficult to understand. We will present the ideas using calculus, and then follow continuous time to discrete time conversion and discretization process to develop tools for discrete signals. This lecture will remind you briefly a few essential things from calculus, namely derivatives and integrals. You're expected to know derivatives and integrals of polynomials, exponential functions, and basic trigonometric functions. Also, you should know basic rules of derivatives and integrals. Let's start with the intuitive meaning of the derivative. Derivative is the rate of change of a given function. In other words, the absolute value of the derivative at a specific point is large if the function is strongly changing around that point, and it is small if the function is not changing very much. The sign of the derivative is positive if the function is growing and negative if falling. Another interpretation of the derivative is local slope of the tangential line. Note that the derivative is not defined for discontinuities or corners. Formally, the derivative is defined as the limit of the ratio, and this ratio is delta x to delta t when delta t goes to 0. Sometimes we will be using symbolics such as dx to dt to show the derivative of x with respect to t, and sometimes we will be using x dot of t or x prime of t. All of them are the same. Now, the intuitive meaning of the integral is even simpler. Integral is an area under the function which could be positive or negative, depends if the function is above or below the horizontal axis. Note that if we will change any finite number of points in the function to some other values, it will not change the integral value. Also, we know about an indefinite integral that it is the opposing operation to a derivative. Formally, the integral is defined by adding infinitesimally narrow rectangles between a and b. Now, if the function is defined in the domain from a to b, for that interval we will define n points, and those points we will call them t1, t2, and so on. Now, the length of each interval will be very, very short, and we will call it delta t. So definitely the number of points will be b minus a divided by delta of t, and each point we will call it t of k. It will be defined as a plus k times delta t. So for example, for k equals 0, we will have point a. For k equals 1, a plus delta t. For k equals 2, a plus 2 delta t, and so on. So for each one of those points, we will compute the value of the function, which is x of tk, and multiply it by delta t. If we add all of those together, this will be our integral. Now, what it all means. X of tk is height of the function at specific point. If we multiply it by delta t, essentially we are finding the area of the rectangle, very narrow rectangle, of width delta t and height x of tk. If we add in all of those rectangles and delta t goes to 0, essentially we're computing integral between a and b of x of t function. Now, this representation is also called Riemann sums. Here are a few examples of derivatives and integrals that you need to know. For example, if x of t is a polynomial with constant coefficients ai, which could be complex or real numbers, then the derivative is given here and the integral is given here. Pay attention that you need to remember those two. For exponential function, similarly, the derivative of exponent is exponent itself, with any coefficient a, which is complex or real exponent of at gives you derivative of a times exponent of at, and integral is exponent of at divided by a plus some given constant. Here are a few more examples of derivatives and integrals for trigonometric functions. Note that if I'm writing that a belongs to complex numbers, it also means that a could belong to real numbers, because this is just particular case of complex numbers. I want to remind you a few derivative properties. First property is the property of linearity. So if you have two different functions, f of t and g of t, and two constants, alpha and beta, and you want derivative of the function alpha f plus beta g, then this is alpha times derivative of f plus beta times derivative of g. The multiplication rule is also very simple. If you want derivative of multiplication of two functions f and g, this is derivative of the first one multiplied by the second one, plus the first one multiplied by derivative of the second one. And now it is very popular to use also chain rule, which is derivative of f of function g of t. So derivative of that kind of function is df to dg times dg to dt. Now let's see some examples of using those rules above. Let's say you want derivative of twice exponent of 2t plus 5t squared. Then you're using just linearity rule, and then you're also using derivatives of exponent and t squared. So derivative of t squared is twice t, and derivative of e of 2t is twice e to the power of 2t, and then you get the result. For the second example of multiplication using multiplication rule, make sure that you understand every step and you can do all of those examples by yourself. The third example is example of chain rule. So if you want derivative of exponent of the t squared, then you define a new function which is t squared, and then you will have derivative of f with regard to d of g, and since f is e to the power of g, this is just e to the power of g, and derivative of g, which is g dot, is derivative of t squared, which is 2t. So you multiply in those two and you get derivative of e to the power of t to the power of 2. Integral properties are also very similar. You have linearity property. If you want integral of alpha times f function plus beta times g function, this is alpha times integral of f plus beta times integral of g. And integration by parts is integral of f derivative times g equals fg minus integral of f times derivative of g. Now, the proof of that integration by parts is very simple, and it's very easy to remember actually. If you remember the rule of derivative of the multiplication of two functions. Basically, if you integrate in both sides of that rule, you get integration by parts. Another property is substitution property. So if you want to define a new function tau, which will be equal to g of t, you can compute integral of f of tau using some other integral, which is f of g times g derivative times dt. Here a simple example. This example uses both substitution and integration by parts. First we are doing substitution. Tau equals to square root of t, from which you can compute that t equals to tau squared, and then the derivative of t with respect to tau is 2 tau. Now, from that, we need to compute dt, because we will need to replace all of the t's in the integral into taus. So we convert dt into twice tau times d tau. So we replace square root of t by tau in the sign inside of the integral, and then multiplying that by twice tau d tau. Now we're using integration by parts, where the first part of the multiplication inside of the integral is function f prime or f dot, and the second one, which is 2 tau, is function g. Using the rule of integration by parts, we're getting the first one is minus cosine tau times 2 tau, minus integral of minus cosine tau multiplied by 2 multiplied by d tau. Now, pay attention that you need to understand all of those steps, so you can stop here and to follow the steps by yourself in a slower pace, that you will understand every single step in that integral, because you might need to compute that kind of integrals in the future. So, the last step will be just replacing every tau by square root of t, and this will be the answer plus constant.